Hello, I'm Jan Kotek, and in this podcast I will give you a quick overview of MapDB, an embedded Java database engine. Traditional Java collections are limited to a few gigabytes by garbage collector and heap size. MapDB provides collections backed by off-heap or on-disk store. Now you can have maps with billions of items. MapDB is embedded database engine. It is written in pure Java, but has performance comparable to native engines written in C. MapDB is very fast and fully concurrent database engine. It is also low level, but very easy to use. MapDB was developed as faster and simple alternative to SQL database. It offers similar features, modes and configuration options. MapDB was originally named JDBM, which means Java Database Manager. This project started 14 years ago, but original database manager goes back in the 70s. I joined JDBM 5 years ago, and since then I released two major versions. About 2 years ago I decided to do complete rewrite to make architecture cleaner and introduce fine-grained concurrency. I also renamed project to MapDB. 1 year ago I quit my daily job and started working on MapDB full-time. And a few months ago, a company called Code Futures offered to sponsor MapDB development. So right now MapDB is open source project with full-time developers and good backing. This project has features usually found in paid products, but MapDB is free as a beer under Apache 2 license. There are no strings attached, everything including documentation and unit test is published. We hope that MapDB will become de facto database engine for Java. MapDB was developed as a hobby project for most of its lifetime, so it has a cleaner and more enjoyable design when compared to similar projects. Most parts were redesigned several times until they were perfect. MapDB has several features. Most importantly, MapDB is fully concurrent with record level locking. Two parallel threads can actually write into underlying files at the same time. Secondly, MapDB offers drop-in replacement for most Java collections. We think it's better to use existing API rather than invent yet another way to access B-trees. If your application has problem with memory, you only have to change a few constructors to move your data off heap or on disk. MapDB was originally designed to run on low-power devices and as such has almost zero internal overhead. It has more than a decade of optimizations, and over time we cut number of abstractions layers to 3, we minimize the data copying, and we use primitive variables for everything to avoid garbage collector thrashing. Also exciting about MapDB is its flexibility. Because of its architecture, it can be used in several modes, from fast alternative to Java collections to in-memory cache or durable database. MapDB has data pump. It allows to stream and filter data from one location to other. Typical use is to import large text files into store. It can create 1 terabyte B-tree with 10 to 12 items overnight. And best of all, MapDB is very small and easy to deploy. It is a single jar file with 40 kilobytes with no dependencies except Java 6. MapDB runs on all Java versions including Android. The entire MapDB codebase has about 12,000 lines of code. MapDB tries to be a universal database engine and it can be used for almost anything, but there are 4 main usages. Firstly, MapDB is often used as off-heap cache. HashMap has expiration based on time to live, time from last access, maximal collection size and maximal memory size. There is most recently used queue for entry expiration. Other use for MapDB is some sort of forklift for big data. Let's say you have a huge file, you need to import it into Hadoop and do some sort of pre-processing before that. With MapDB you could filter and pre-process this data file on single computer. You could also do prototyping before writing full-scale clustered algorithm. MapDB can be also used as traditional database. It has ACID transactions with proper isolation and write conflict resolution. However, MapDB is still a young project, and people tend to be conservative about their databases. And last but best is MapDB as an alternative memory model. If you are limited by garbage collector to few gigabytes, you can switch your data model completely into MapDB to avoid this limitation. We have maps, list, atomic variables, references, and so on. You can preserve your state between JVM shutdowns very easily. We also have Java. You can also keep using concurrent Java utilities such as logs, queues, and so on. Our test shows that compared to Java heap, MapDB is twice slower, but fits 3 times more data in the same store. It also doesn't have a limitation imposed by garbage collector, so around the size of 16 gigabytes is actually faster. MapDB has highly modular architecture. Every component can be completely disabled, so there is no overhead for unused features. Each component has several implementations. For example, there are 5 different cache implementations and 3 different storage formats. Also, data types such as maps or queues are separated from the rest of the systems. They have a swappable backend, so the same collection can be used in many cases or many scenarios with different durability implications. And best of all, MapDB's architecture is very friendly to developers and hackers. It is very easy to develop new components. For example, default cache has only 50 lines of code, but is fully concurrent. Also, collections are easily portable from traditional Java heap. You only have to replace allocation and reference calls to use MapDB. For example, queues were ported from Java collection framework in 1 day. Most advanced collection offered by MapDB is B3 map and set. It is optimized for a large number of small keys. It fully implements concurrent navigable map and navigable set. It is based on B plus link 3. This data structure is almost log-free and offers great concurrent scalability. It is used in PostgreSQL and other SQL databases. MapDB offers data pump for this collection. It is a fast way to import data from an iterator. It builds leaf nodes first, and then build directory nodes on top. Import time in this case is linear, so 1 terabyte B3 can be created overnight. To minimize space consumption, we use delta key compression. For example, for numbers, we store only first number and then difference between the numbers because they are sorted. For strings, we store only the first string and then use common prefix compression. We have several data key compressors for arrays, tuples, and so on. MapDB also has good support for composite hierarchical keys, so you can compose various types of indexes using B3 map. Another data type offered by MapDB is hash map and hash set. It is optimized for large keys, and it has optimal and optional entry expiration based on several criteria. It is very easy to use for cache. Also, it uses hash tree table, so it doesn't need rehashing or other similar collections. There are several queues implementation. We have a FIFO, LIFO, circle queues with fixed size. Some of them are log-free, some optimized for single producer and vice versa. Single producer and multiple consumers and other way around. It is also very easy to write new queues for MapDB. MapDB also has atomic variables. They store their state in database and the values are persisted between JVM shutdowns. So atomic variables are a very easy way to port Java code into the Java code from Java heap to MapDB. Most databases expect user to perform serialization and pass already serialized data into database. Even SQL has its own format. MapDB on the other side takes that data in user format and also takes serializer which turns data into binary form. The major difference can be seen here. Most databases just expect some sort of pre-processed data, but MapDB takes the data themselves and some sort of callback interface which turns data into binary form, from and into binary form. It is small detail, but it makes MapDB highly modulable and flexible. For example, data with serializer can be forwarded to background thread for asynchronous serialization. The deserialized data can be also stored in cache to minimize deserialization overhead. Engine wrappers engine is primitive key value store. It has operation for creating, removing, and updating and deleting records. It's a centerpiece of MapDB design, and the data model such as B3 sits on top and the low-level storage sits beneath it. Most features in MapDB are implemented as engine wrappers. For example, a read-only wrapper blocks calls, which will modify underlying store and throws an exception instead. Caches, asynchronous writes, or even encryption can be implemented similar way, or is implemented similar way. MapDB has an abstraction layer over raw devices such as memory blocks, files, or even raw disks. There are several implementations which include byte arrays, off-heap byte buffers, random access files, and memory map files. We also work on support for accessing raw disks to avoid file system overhead. This abstraction can be also extended to support features similar to RAID, such as data duplication, sharding across multiple disks, control checksums, and so on. MapDB evolved from low-level store, so it supports most transactional modes. 3 modes are most important. First, there is direct mode, which is used when transactions are disabled. In this case, the changes are written directly to store. It is very fast, but there is no protection from data corruption. It is very important to close store correctly. This mode is usable for in-memory operations, temporary disk collections where the preservation doesn't matter, or for very fast imports because it shares the same format with other stores. Second mode is very similar to the direct mode, but it uses single global transaction. In this case, the store is protected by write-ahead lock or append-only file. This sort of protection is very similar to SQL databases and other key-value databases. Because there is only one transaction at a time, we do not have to worry about concurrent modifications and write conflict resolutions. Third mode are full concurrent transaction. It offers a serializable isolation level with optimistic locking. This is strongest isolation level. It even keeps track of records read by other transactions. So if you have, for example, if you have 2 transactions, one of them is modifying data, second one is doing some sort of checks, some sort of aggregate on top of the data. The second transaction will not store the incorrect aggregate because it will be rolled back when the data are modified by the first transaction. Conflict resolution is done in memory with very small overhead. So if transaction is rolled back due to conflict, it doesn't even touch the disk. The concurrent transactions in MapDB are very fast, yet there are no compromises with isolation levels and durability. In near future, we are going to improve speed even more. Various versions of MapDB were under development for more than a decade. Now, after rewrite, it has features of proper database with speed of low-level store. It is very exciting to have a first stable release scheduled in just a few weeks. There is strong commercial company sponsoring MapDB development, so in future we will probably offer commercial support, training, and consulting. Other goals for future is to improve MapDB tooling and its internals. There are several ways to improve speed and add some interesting features. Also, we have a lot of ideas for how to improve concurrent transactions and snapshots. Users were asking for more collections, so soon we will add a packed bit set to handle Bloom filters. Also, we will add an alternative to array list called index.tq. We also have some plans for networking. Users were asking for server-client implementation and replication. There is a lot of stuff happening in Java 8, and MapDB will have a first-class support for lambdas and streams. Java 8 support will be added in separate project, so we will not have to drop support for Java 6. We will keep supporting Java 6 for a long time. And most importantly, MapDB will extend its data pump. It will be able to perform most database operation in streaming fashion, and this will enable for MapDB to handle huge data sets on single computer. That's all for now. For more information, you can visit our website at mapdb.org or visit our sponsors at codefutures.com. You may also contact me directly at jan@kotek.net, and my Twitter ID is jankotek. Thank you all for listening and have a nice day.